Hi, good afternoon. So we'll wait for one more minute and we'll start. So yeah, okay, we'll start now. Just a minute. Okay, yeah, we'll start now. So yeah, I welcome you all once again to the problem solving session for the NPTEL course Computational Fluid Dynamics. So the course code is NOC 25CH18. Course instructor is Professor Sreenivas Jayanti sir from the Department of Chemical Engineering IIT Madras, and myself Ankar Kartika, a research scholar from Department of Chemical Engineering IIT Hyderabad. So I'll be handling the live sessions every Saturday from 3 p.m. to 5 p.m. So in these sessions, as we all know, we have been seeing the problems related to that week's assignment, so that it will help you guys in solving the assignments. So now we are into week 5, and we'll start the session. So as you all know, it is a 12 weeks course, and by now we are familiar with the course layout, wherein in the first 2 weeks we saw about the calculation of flow in a rectangular duct and in a triangular duct, and later in week 3 it was about derivations of equations governing fluid flow, and equations for incompressible flow and boundary conditions. And in week 5, that is this one, it is basic concepts of CFD, finite difference approximations, and later it would be like some concepts like consistency, stability, and convergence associated with CFD. And later on, till now we have seen about what are all the equations governing the fluid flow. Mostly the equations we will be solving when we are using the cold flow system is mass conservation, that is continuity equation, and momentum conservation equation. So altogether, if it is a 3D system, we will have 4 equations. And in addition to normal cold flow, if any other energy exchange or reactions are taking place, we solve additional equations based on that, like energy equations and species balance equations. Those things we have seen in the last class. So in today's class, it is about the finite difference approximation, like concepts like forward difference, central difference, backward difference, and first order, second order, those things. And once we are familiar with these concepts, we will see how to solve the Navier-Stokes equations, because our ultimate aim is to solve those equations when we are dealing with the fluid flow. So we can get an estimate of the fluid flow variables like velocity, pressure, and if any energy exchange is taking place, we also get to know the temperature at that point. So to know that, we need to know how to solve Navier-Stokes equations, because those are a coupled system of equations. It is not very easy to solve those equations. So solution of Navier-Stokes for compressible flows as well as incompressible flows. And it would be finally it was about solution of linear algebraic equations, because we are converting the partial differential equations into linear algebraic equations by using discretization schemes like finite difference approach or finite volume or finite element approach, which we will not be mostly dealing with. But we are converting PDEs into linear algebraic equations, and we must know the numerical techniques to solve those equations. So that is will be covered in basic methods and advanced methods. And finally, it is about finite volume methods and grid generation. And lastly, it is about turbulence flows. So this is just to give you an idea of where we are at the point and how far we have come and what are all the things we will be covering in the future. So moving on to books and references, we have 5 books. First is Ferziger and Perry Computational Methods for Fluid Dynamics, and second is Hirsch Numerical Computation of Internal and External Flows, and third one it is Patankar SB Numerical Heat Transfer and Fluid Flow. Fourth one it is Verstig and Malal Sekara, an Introduction to Computational Fluid Dynamics Finite Volume Method. And last it is Anderson JD Computational Fluid Dynamics Basics with Applications. So now we are in week 5 problems. So in today's, before going to the problems, I'll just give you an idea of the equations like Taylor series expansion and what finite forward difference, backward difference and central difference schemes equations come around as. So first one, when we are using Taylor series expansion, we have for point f x plus delta x expansion, we have it as f of x at x plus dou f by dou x at x into delta x plus dou square f by dou x square into delta x square by 2 factorial, and it moves on till dou n dou to the power nf and divided by dou xn at x into delta x to the power of n divided by n factorial. So we take number of terms depending on our interest and the problem under specified conditions. So based on that we move. So it is the expansion for f of x plus delta x. So for that we have this expansion, and from this what we can get is that when this f of x goes to the other side and we are ignoring all the terms. So what do we get? Dou f by dou x equal to f of x plus delta x minus f of x at x divided by delta x. So dou f by dou x at x equal to f of x plus delta x minus f of x divided by delta x plus it is of the order of first one, because like if after this we are just when we are considering all the left out terms, the first power is delta x. So if we divide this equations in general, what will we have? We will have f of x plus delta x divided by x equal to f of x by delta x plus dou f by dou x plus dou square f by dou x square into delta x by 2, because we are dividing by 2. Sorry, we are dividing by delta x, we will be left out with one power only. So we can say that the minimum power is here is like delta x is raised to the minimum power of 1 in the remaining terms that we are not considering. So we are calling it as a first order term, like rest of the things. So it is first order. Similarly, when we have f of x minus delta x expansion using Taylor series, what will we have? We will have it as in place of delta x we will be using minus delta x. So we have f of x minus delta x equal to f of x at x minus dou f by dou x at x into delta x plus dou square f by dou x square into delta x square by 2 factorial and so on. Here what happens is that it minus 1 to the power of n into dou n to the power of n f divided by dou x n at x into delta x n raised to the power of n divided by n factorial. So what things we need to note here is that because we are using minus here, the all the odd terms like wherever the delta x is raised to the power of odd numbers, it will have negative sign. So from here what can we get? We can get dou f by dou x at x equal to this, let it go this side and that it will come this side. So what happens? F of x minus delta x, and we will divide it by delta x. So it is giving rise to backward formula. So backward difference approach we are getting from this as dou f by dou x at x equal to f of x minus delta x divided by delta x plus order of again it is first order difference. So this is we now till now we have seen about forward difference and backward difference. Now we have central difference scheme. So central difference formula I am directly giving it over here. So it is dou f by dou x at x equal to f of x plus delta x minus f of x minus delta x divided by 2 into delta x plus it is of the second order because the power is raised to 2 to the power of 2. I mean the truncation error terms are raised to the power of 2. So we are calling it as second order. So this is just to give you an idea of what the forward difference, backward difference and central difference formula look like. So now we will move on to problems. So first problem is that we have one figure. So okay. So for the first question what we have is that which of the following statements is true about the grid shown in figure 1? So this is figure 1. So what are we seeing? It is j is equal to 1, 2, 3, 4 and I is equal to 1, I minus 1, I plus 1. So that's what we have. So there are a few statements which are given over here and we need to identify which of them are true. So which of the following is true about the grid shown in figure 1? So that is question, and we'll see the statements first. First statement, it is mentioned that it is an unstructured grid. It is an unstructured grid. Second statement, it is given that it has uniform spacing in both horizontal and vertical directions. And third one, it can be used for finite difference methods. So these are the three statements that are given and we need to identify which of the following are true. So going about, what is the first statement? First statement, it is stating that it is an unstructured grid. But is the grid unstructured? No, we know it is not unstructured grid and it is a structured grid because it is like incrementing and it is very even having uniform spacing in the x direction and uniform spacing in the y direction separately also. So it is a structured grid. There is no unstructuredness in this grid, and so first statement is false. Second statement, it is saying that it has uniform spacing in both horizontal and vertical directions. So if we see, this is a horizontal direction and the spacing is uniform. Similarly, if we see in the vertical direction, again the spacing between grids is very uniform. So this statement is true. Third one, it can be used for finite difference methods. So yeah, this grid can be used in the finite difference methods. So third statement is also true. So first one is false because this grid is a structured grid. First statement is false. Second statement, it is true, and third statement is also true. So now we will look at the options. Options are option A, one only, option B, Option B 1 and 2. Option C 2 and 3. Option D 1, 2 and 3. So now we know that first statement is false and second and third statements are true. So option C is the right answer, because this grid is a structured grid and it has uniform spacing in the vertical and horizontal directions, and third one, it can be used for the finite difference methods. So those are the three statements, but in the given context, first one is given as unstructured grid, so first statement alone is false, rest of the 2 and 3 are true. So option C is the right answer. Option C 2 and 3 is the right answer. Now we will go to question 2. In question 2, again the question is based on the same figure, that is figure 1. In figure 1, the dark thick line indicates the boundary of the computational domain. So what is that? The dark thick line. So it is these three lines denotes the boundaries of the computational domain. Which of the following is a Dirichlet boundary condition on the side AB? So this is side AB, and we are surrounded like these three are the boundaries in the computational domain, and we need to identify what is a Dirichlet boundary condition. So what is Dirichlet boundary condition? Dirichlet boundary condition is nothing but the condition which specifies the values for that variable. So if we specify the values for that variable, we call it as a Dirichlet boundary conditions. Whereas if we are specifying the value for the derivative of the variable, we call it Newman boundary condition. I'll give you an example. Like for example, consider a pipe flow only. In pipe flow, we can say that in one end, we are just heating and we are giving some fluid flow as well. So in that case, what can we say about that? Like we can say that velocity equal to some 2 meter per second. Velocity is equal to 3 meter per second. So if, and temperature is equal to 273, temperature is 300. Like that, if we are giving some values, we call it Dirichlet boundary conditions. So in the similar manner, in the end of the pipe, it is insulated. So there is no heat transfer across the system. So like those things can be like temperature is not escape. I mean temperature there like we can say that the temperature gradient is 0, or temperature gradient is so and so value. If in those cases, if we are specifying it as that, like that, we call it Newman boundary condition. So we'll look at the options first. So which of the following is a Dirichlet boundary condition? Now we need to identify which of the following is a Dirichlet boundary conditions. Dirichlet boundary condition specifies the value for that variable. So first one, it is u equal to 0, and second one t is equal to 273, and third one, it is adiabatic boundary. So looking at that, we can say that, I mean before options itself, what can we say about this? We can say that u equal to 0 is a Dirichlet boundary condition, and similarly t is equal to 273 is also a Dirichlet boundary conditions. Why? Because we are specifying the value of that variable in the boundaries. So we are giving some values, so it is a Dirichlet boundary conditions. Whereas adiabatic boundary conditions, what does it specify? That it is, there is no exchange with the surroundings. So in that cases, we use the gradient terms, like there is no exchange with the surroundings, so we cannot specify it as a value, rather we give it as a gradient. So that adiabatic boundary condition is a Newman boundary condition. So now we will look at the options. Option A 1 only, option B 1 and 2, option C 2 and 3, option D 1 and, oh, two options are 1 and 2 actually, but yeah, fine. Option 1 and 2 is the right answer, but it can be B or D, it doesn't matter. Option D, like, so we can change it actually, like, just for our sake. So option D is the right answer. That is 1 and 2 is the right answer. Wherein we are giving the values for velocity and values for the temperature. So 1 and 2 is the Dirichlet boundary condition. So option D, 1 and 2. Dirichlet boundary condition specifies the value to the variable and Newman boundary condition specifies the value to the derivative of the variable. So I hope now it is clear. Now we will go to question 3. Question 3, it is about a figure, this particular figure, and we'll see the question first. Which of the following statements is false? Which of the following statements is false about the discretized equation having the computational molecule shown in figure 2? Okay. Okay. We need to identify which of the following statements are false. So there are few statements given. First we'll read the statements. First statement, it is saying that the algebraic equations will have at most 5 variables. Second statement, algebraic equation will have at least 5 variables. And third one, coefficient of the variable value I comma j, variable value at I comma j will be at least equal to the sum of the magnitudes of the coefficients of the other variables. Okay, these are the three statements. Now we need to identify which of the following statements are false. First, we'll go through the statements one by one. In the first statement, what it is given that the algebraic equations will have at most 5 variable values. So this is the computational domain that is given. So if we are doing anything at I comma j, we will have I minus 1 comma j, I plus 1 comma j, j minus 1 comma I comma j minus 1 and I comma j plus 1. So the discretized equation, if this computational molecule is this, we can have maximum 5 variables in the equations. But if this is the boundary or this is the boundary, the number of variables will reduce because we will be specifying the values. So max to max it can have 5 variables in the equations for this computational molecule. But if any boundaries are included or anything else, the number of variables will reduce. So first statement is a true statement. Second statement, algebraic equation will have at least 5 variable values. So it is saying that none of them will go as values, rather all the variables will remain as variables. That is what is given in second statement. But that statement is false. Why? Because if it is a boundary, again we know that it becomes values and maximum it can have 5, but minimum it cannot be 5. Minimum it can be anything less than or the value can be less than or equal to 5. So we cannot say minimum 5 will all 5 all 5 will be variables. We cannot make statements like that. So second statement is a false statement. Coming to third statement, coefficient of the variable value at I comma j will be at least equal to the sum of the magnitudes of the coefficients of the other variables. Again, this is false. Sorry. This is false because like we cannot again say that as a sum of the magnitudes of the coefficients of the other variable values. So 2 and 3 are false whereas 1 is true. So we'll see the question is about which of the following statements is false. So whenever we are reading the question, make sure you read the question properly. It can be true or it can be false. So you should be prepared to answer those questions clearly. So take time to read the questions. So options are option A 1 only, option B 1 and 2, Option C 2 and 3. Option D 1, 2 and 3. So since the question is about which of the following statements is false, we can rightly say it as second and third statements are false. So the answer to this question is option C, that is 2 and 3 is the right answer. Which of the following statements is false about the discretized equation having computational scheme shown in figure 2? So first statement, algebraic equations will have at most 5 variables is true. Second one, algebraic equations will have at least 5 variables, that is false. Similarly, coefficient of variable value at I comma j will be at least equal to the sum of the magnitudes of the coefficients of the other variable values. Again, third statement is false. So second and third are false, one alone is true. So option C is the right answer. Answer is option C, 2 and 3. Okay. Now we will move on to question 4. Again, the question 4 is based on this particular figure. Now what is asked? From the discretization of which of the following equations will a computational molecule of the type shown in figure 2 be obtained? So this is figure 2. So this is the computational molecule. So this computational molecule includes I comma j point, I minus 1 comma j point, I plus 1 comma j point, and similarly I comma j minus 1 point, I comma j plus 1 point. So 5, these 5 terms are included. So the question is, from the discretization of which of the following equations will a computational molecule of the type shown in figure 2 be obtained? So now we need to identify for which of the equations when getting discretized we will get this particular computational molecule, including these 5 points. So we'll see the options first. Option 1, it is one-dimensional Poisson equation, and second one, it is two-dimensional Poisson equation. Okay. Okay. We have two options. Option 1 is one-dimensional Poisson equation, 2 is two-dimensional Poisson equations. So first one, when we look at the figure itself, we can say that it is a two-dimensional figure. So we need to identify whether it is this particular Poisson equation when discretized will give rise to computational molecule of this type or not. So straight away we can say first statement is false, but we need to check about the second statement. So now we'll see the options first. Option A 1 and 2, option B 2 only, option C 1 only, option D none of the above. So we first option A and C are false, and we need to choose one between B and D. So if we say about Poisson equations, it has dou square f by dou x square plus dou square f by dou y square. So we need to when expanded it will give rise to this structure actually. So answer is actually option B is the right answer. So we'll see that discretization of the Poisson equation in this slide. So Poisson equation is given as dou square f by dou x square plus dou square f by dou y square equal to f of x comma y. So when we are using central difference scheme for the dou square f by dou x square, what are we getting? We are getting this particular expansion, f of x minus delta x minus 2 times of f of x plus f of x plus delta x divided by delta x square. Similarly, for dou square f by dou x square at y gives rise to f of y minus delta y minus 2 times of f of y plus f of y plus delta y divided by delta y square. So when we see, we have x minus delta x, x and x plus delta x. Similarly, y minus delta y, y plus delta y. So all the components in the computational molecules are included. So we can say that it is a two-dimensional Poisson equation. So I minus 1, I plus 1, similarly j minus 1, j plus 1. So this computational molecule is included when we are discretizing the two-dimensional Poisson equation. So answer is option B. So that is question 4. Now we will look at question 5. So question 5, it is about, again some figure we got, figure 3, and sorry, if we write a Taylor series expansion for f of I minus 1 comma j about point P in figure 3, then the third term in the expansion is given by dash. If we write a Taylor series expansion for f of I minus 1 comma j about point P in figure 3, then the third term in the expansion is given by dash. So it is a Taylor series expansion. So we'll see the options first. Option A, it is minus 1 by 2 into dou square f by dou x square at P into delta x square. Option B, it is minus 1 by 6 dou cube f by dou x cube at P into delta x cube. Option C, it is 1 by 2 dou square f by dou x square at I minus 1 comma j into delta x square. Option D, none of the above. So if we expand f of I minus 1 comma j, what will we get? It will be like f of I minus 1 comma j at point P. So it will be like f of I minus dou f of I at P So if we write a Taylor series expansion for f of I minus 1, what will we get? We will get f of I at P minus dou f by dou x at P into delta x plus dou square f by dou x square into delta x square by 2 factorial at point P. So first of all, the third term will not have a negative sign because it is like minus delta x to the power of 2. So it becomes positive. So first two options are wrong basically. Third one, it is 1 by 2 into dou square f by dou x square at I minus 1 into delta x square. It is not at I minus 1, it is about point P. So it is at point P. So it should be at point P, it shouldn't be at I minus 1 comma j. So option C is also false. So answer is none of the above. Option D is the answer, none of the above. Why? Because f of x minus delta x is given by f of x at x minus dou f by dou x at x into delta x plus dou square f by dou x square into at x into delta x square by 2 factorial and goes on. So here f of I minus 1, so it is f of I, we can keep at I minus dou f by dou x at P into delta x plus dou square f by dou x square into delta dou square f by dou x square at P into delta x square by 2 factorial. So it is wrong because it is given as I minus 1 comma j. Rather it should be at P. So that all three given are wrong and option D, none of the above is the right answer. Now we will go to question 6. Question 6 involves the same figure, that is figure 3. Now, with respect to figure 3, that is this figure, for discretization of which of the following at point P may we get one or more of the corner points A, B, C, D. So, when we are discretizing some things which are given over here at point P, where we will get the inclusion of A, B, C and D, these corner points. So that is the question. Now we will see the options first. Option A, it is dou square u by dou x square plus dou square u by dou y square. Option B, it is dou square u by dou x dou y. Option C, dou square u by dou y square. Option D, dou square u by dou x square minus dou square u by dou y square. So when we are expanding dou square u by dou x square, we all know that we will include I minus 1 comma j, I comma j and I plus 1 comma j for x and j minus 1 j plus 1 for y. So for the second order derivative, that is dou square u by dou x square or dou square u by dou y square, with expansion we will be having this particular thing only. Like how we, not this, how we saw in previous problem, we will be including this domain. So that is wrong. So that is a wrong thing, because we are just asked to find which of the discretization will give us corner point A, B, C and D. So pure derivative, second order derivative is not giving us. So we are going with the mixed derivative. Dou square u by dou x dou y. Option B therefore will give us. So we can rule out the rest and we will get one option, that is option B. So answer is option B, dou square u by dou x dou y. So now we will just confirm with our options through proper expansion and method. So we'll see the solution actually. Dou square u by dou x square at I comma j is given by u at I minus 1 comma j minus 2 times of u I comma j plus u at I plus 1 comma j divided by delta x square plus order of delta x, second order. Similarly for y derivative, if it is dou square u by dou y square at I comma j, we will have u at I comma j minus 1 minus 2 times of u at I comma j plus u at I comma j plus 1. So here we are varying with respect to y position. J minus 1, j plus 1 divided by delta y square, and it is also second order. So mixed derivative, that is dou square u by dou x dou y, we have it as this particular expansion. U at I plus 1 comma j plus 1 minus u at I plus 1 comma j minus 1 minus u at I minus 1 comma j plus 1 plus u at I minus 1 comma j minus 1. So for I, I'll do one thing. This. So we have I plus 1 comma j plus 1, I plus 1 comma j plus 1, C, I plus 1 comma j minus 1, B, I minus 1 comma j plus 1. So we have D, I minus 1, j minus 1, E. So we have one or more corner points. So it is given from dou square u by dou x dou y. So again, if the other options like dou square u by dou x square plus dou square u by dou y square, or dou square u by dou x square minus dou square u by dou y square, it will basically give us this terms only. There is no possibility of getting the corner points. So the answer is dou square u by dou x dou y is the answer. We can actually go about that as like these things we remember. If we want to get it get the expansion, we cannot remember most of the time. So what we can do is dou by dou y of dou u by dou x. So it is dou by dou y of dou u by dou x, right? So it is, we are using forward difference approach, and it is u at x plus delta x minus u at x divided by delta x, and we are just expanding that, and we are getting it as u at x plus delta x at and y plus delta y minus u at x plus delta x at y divided by delta x delta y minus u at x comma y plus delta y minus u at x comma y. So yes, something is missing actually. So I did something wrong. Okay, this is one way, that is one way. Whichever way you go about, you will have at least one of the one or the corner points. So that's it. With respect to figure 3, for discretization of which of the following points at point P may we get one or more of the corner points A, B, C and D. So it is dou square u by dou x square plus dou square u by dou y square, we are not getting any corner points. But for dou square u by dou x dou y, we are getting corner points. And similarly dou square u by dou y square, we are not getting any corner points. Or if we go with dou square u by dou x square minus dou square u by dou y square, again we are not getting any corner points. So answer is option B is the right answer. So answer is option B, dou square u by dou x dou y. So that is we have seen. Method is same, but maybe some equation might be wrong, but yeah, let's not worry about that. But when you are doing mixed derivatives, you will get the corner points like how we got it here. So that is a takeaway here. Now we will go to question 7. So in question 7, what we have some structured grid, but this grid is not uniform. The spacing is not uniform. So we'll see that. We'll see a question first. In the question, what is asked? Which of the following options is correct with respect to the grid shown in figure 4? So this is figure 4, and which of the following options are correct? So first one, it is a uniform grid. So it is a non-uniform grid, it is not uniform. So answer is, first statement is false. Second one, it is given that finite difference method cannot be used for this grid. Again, this is false because we can use finite difference method. And third one, it is finite volume method can be used for this grid. So yeah, we can use finite volume method for this as, we can use finite volume method. So we can use finite difference or we can use finite volume, it doesn't matter. So we'll see the options first. Option A 1, option B 1 and 2, option C 1 and 3, option D it is 3. So like if we look at the statements, first statement it is given that it is a uniform grid. So basically the grid is not uniform because as we can see the spacing is very irregular in this, but it is a structured grid. It is a structured grid, but it is a non-uniform grid. So first statement is false. And second one, what is given? Finite difference method cannot be used for this grid. So this is false because we can use finite difference for this problem as well. and we can use finite volume method as well. So second statement is false because it is given, it cannot be used. And third statement, it is true because finite volume method we can use. So out of the options, if we look at, one is present in three options. So it is actually three options are wrong because one is false. Only third statement is right. So option some for the seventh question, the right answer is option D. That is third statement is the only right statement. What is given in third statement? In third statement, we have given that finite volume method can be used for this grid. So that is the only right statement. The rest of the statements, if it had been like it is a non-uniform grid, or if it is given like finite difference cannot be used, finite difference can be used. So if it had been given like that, it would have been right. But it is not given. So the right answer is option 3 only. Also, while reading question, here it is asked which of the following statements is correct. If the question is asked like which of the following statements is wrong, so it should be like 1 and 2. So we should read the question properly. But for this question, it is clearly asked that which of the following options is correct with respect to the grid shown in figure 4. So only right statement is option 3. Finite volume method can be used for this grid. So option D is the right answer. So option D is the right answer. Now for question 8, again we are going with figure 4 only. In figure 4, what is given? Which of the following is false about central difference approximation of the first derivative at point I on the grid shown in figure 4? So here again the question is about which of the following is false. It is not about which of the following is true. So which of the following is false about the central difference approximation of the first derivative at point I on the grid shown in figure 4. So we'll see this options first. First one, it will involve points I minus 1, I plus 1. So that is true. It is about, it will involve points I minus 1 and I plus 1. Second one, it will be formally second order accurate only if x at I minus x at I minus 1 divided by x at I plus 1 minus x at I is less than 1. This is false because like values are not deciding the second order accurate or first order accurate. It all comes from the derivation. During derivation, if what are all the terms that is being neglected or reduced as, I guess it is a truncation error something. So which are the terms we are reducing to? So what is the power of the first term? So that only decides the order of accuracy of that approximation. So second statement is false, whereas first one is true, second statement is false. We will look at the options now. Option A 1, option B it is 2, option C it is 1 and 2, option D it is neither 1 nor 2. So we all know now that first statement is true statement, second statement is false statement. Which of the following is false about central difference approximation of the first derivative? It will involve points I minus 1, I plus 1. So central difference approximations, obviously it will involve all 3 points. So that is central difference approximation of the first derivative. That is dou f by dou x. So that is what we have seen in the first slide, right? Dou f by dou x at x. So it is at x. So it is f of x plus delta x minus f of x minus delta x. So it is involving the equation at I and involving points I minus 1, I plus 1. So it will be formally second order accurate if this condition is satisfied, but it is already like second order accurate, and it doesn't depend on this particular condition. So as we mentioned, like order of accuracy, it doesn't come from this. So options are option A. So answer is option B is the right answer. B2 is the right answer. Now we'll go to question 9. In question 9, what is asked? For what value of Q is the following a second order accurate approximation? For what value of Q is the following a second order accurate approximation? So just 1 minute. Okay, we'll see. D cube f by dx cube equal to minus 3 f at I plus 4 plus 14 into f at I plus 3 minus 24 into f at I plus 2 plus q into f at I plus 1 minus 5 at f at I divided by 2 into delta x cube. So we need to find the value of q for the following second order accurate approximation. So the thing is, we are writing the discretization of the d cube f by dx cube, and the equation is second order accurate, and we need to identify the value of q. So we'll see the problem. So options are option A 12, option B 14, option C 16, option D it is 18. So I'll go with the answer first because it is a problem. We will see how to derive that in the coming question. So answer is option D is the answer. Option D 18 is the answer. So we'll see how it is 18. So first we'll write few things. F at x plus I. So the derivation is given by f of x plus f dash of x into delta x plus f double dash of x into delta x square by 2 factorial plus f triple dash of x into delta x cube by 3 factorial and so on. Similarly, f at f of x at I plus 2 is f of x plus f dash of x into 2 times of delta x plus f double dash of x into 2 times of delta x the whole square in by 2 factorial plus f triple dash of x into 2 times of delta x to the whole power of 3 in divided by 3 factorial and so on. So and so on, like the expansion will go on in that fashion, that like f of x at I plus 3 will be like f of x plus f dash of x into 3 times of delta x plus f double dash of x into 3 times of delta x the whole square divided by 2 factorial and so on. So that is the thing. Now what will we do? We'll write d cube f by dx cube. So it is f triple dash of x and it involves these terms, right? Like f of x at I plus 1, f of x at I plus 2, f of x at I plus 3, f of x at I plus 4 and f of x at I divided by delta x cube equal to 0. So this is the general format of the equation. This is given in the question as well. So for now we will assume all the coefficients as a0, a1, a2, a3 and a4. So we are giving some generalized equations and the format is the general format and it is given in the question as well. But rather than the coefficients given in the question, what we are doing, we are just taking the a0, a1, a2, a3 like that. So now we have we'll write everything out. So first for r is we are just multiplying by delta x cube. So it becomes f dash of x into delta x cube and this delta x cube goes away for r is and for right now only. So it is f triple dash of x into delta x cube minus a0 into f of x at I. F of x into I plus 1. So it is f of x plus f dash of x into delta x plus f dash of x into delta x square by 2 factorial. Sorry. Yeah, for now we are writing all the terms. Later we can while simplifying we can simplify the rest. F of x plus f dash of x into delta x plus f double dash of x into delta x square by 2 factorial plus f triple dash of x into delta x cube by 3 factorial plus f 4 to the power of fourth power of x into delta x to the power of 4 by 4 factorial. Because it is given from x I plus 1, I plus 2, I plus 3, I plus 4, we are taking till these terms. And similarly for we are writing for a1. So it is minus is common. So yeah, a0, okay, this should be, this minus shouldn't be common. It should be like, no, not there. Here it should be plus and here it should be minus. So we'll go one by one first. It's from first. So we are just writing the expansion of f of x at I plus 1 and similarly how it will look for f of x expansion at I plus 2 and we are written the equation. Similar things we can write for f of x at I plus 3 and f of x at I plus 4 as well. And the generalized equation for d cube f by dx cube is written as this. and it is got from the question as well. So f triple dash of x minus a naught into f of x at I plus 1 plus a1 into f of x into I plus 2 plus a2 into f of x at I plus 3 plus a3 into f of x at I plus 4 plus a4 into f of x at I divided by delta x cube. So these are just coefficients for our understanding. Coefficients can be anything. So we know the value of 4 of these coefficients, only one is unknown. So for that, what we are doing, we are just taking the delta x cube and multiplying through the whole equations. So and we will get f triple dash of x into delta x cube plus, because the minus is going into each and every term inside, so it is minus a naught into f of x, like we are just substituting the whole equation in this, a naught into f of x at I plus 1 minus a1 into f of x at I plus 2 minus a2 into f of x at I plus 3. So here we can see that it is a, here it is delta x, here it is 2 times of delta x, here it is 3 times of delta x minus a3 into it is 4 times of delta x. So we are just substituting, and at last minus a4 into f of x. So f of x at I, so it is f of x. So we are just substituting everything back in the equation. So substituting the expansion terms in the equation. So this is the equation which we will be getting. So now what we are doing is that we are taking the coefficients common and writing it like this. For now it is f of x we are taking, and we are getting the coefficients as minus a naught minus a1 minus a2, and here it is minus a3, and here it is minus a4. Similarly, for f dash of x into delta x, what coefficient we have? Coefficient is minus a naught, and here we have minus a1 into 2, and here it is minus a2 into 3, and here it is minus a3 into 4, and yeah, that's it, minus 4a3. Similarly, now we are having f double dash of x into delta x square by 2, and we have minus a naught, again we have it is minus 4a1 minus 9a2, like here it is 2 power of 2 square, so it is 4, and here it is 3 square, so it is 9. Similarly, it is 4 square equals 16. And what else? We have f triple dash of x. For that we have delta x cube, right? So we are having taking delta x cube by 3 factorial. So in the question itself we have 1 delta x cube. So we are having, since we are taking 3 factorial common, we are multiplying by 3 factorial. So 3 factorial minus a naught minus 2 to the power of 3 into a1 minus 3 to the power of 3 into a2, 3 to the power of 3 cube, and here it is a3 into 4 to the power of 3. Similarly, last term we have f to the power of 4 at delta x square x power 4 by 4 factorial, and we have minus a naught and 4 power 2, 4 power 3, 4 power 4. So these are all the coefficients we have. Now what we are doing, we have got the equation. So now we are solving for it. So each coefficient is like equal to 0. So we are just solving the equation. So for the first we have minus a naught minus a1 minus a2 minus a3 minus a4 equal to 0. And second we have minus a naught minus 2 times of a1 minus 3 times of a2 minus 4 times of a3 equal to 0. And for the third one we have minus a naught minus 4a1 minus 9a2 minus 16a3 equal to 0, like everything is squared over here. And for the third one we have 3 factorial minus a naught minus 8a1 minus 27a2 minus 64a3 4 cube. So and last we have minus a naught minus 2 to the power of 4, 2 to the 4, 4 4s are 16, and 3 to the power of 4 and 4 to the power of 4. So we have 5 equations now, 1, 2, 3, 4, 5, and okay, no. Okay, we have 5 equations and 5 unknowns, A0, A1, A2, A3, A4. Right, A0, A1, A2, A3, A4. So 5 equations and 5 unknowns. So these equations can be solved directly through some numerical means or something, and matrix things also. And what factor we will get is A0 equal to 9, A1 equal to minus 12, A2 equal to 7, A3 equal to minus 3 by 2, A4 equal to minus 5 by 2. So we have 5 unknowns which we got by solving these 5 equations simultaneously. So solving the 5 equations simultaneously will give rise to the solution for the 5 unknowns. So now we are substituting these these values which we calculated back in the equation. So f triple dash of x minus 9, okay, yeah, it is minus whole and values are only a0. So in this equations we are substituting the values of a0, a1, a2, a3, a4 which we got, and substituting back in the equation gives us values. So it is f triple dash of x minus 9 times of f of x at I plus 1 minus 12, okay, it is x minus 12 into f of x at I plus 2 plus 7 into f of x at I plus 3 minus 3 by 2 into, oh my goodness, minus 3 by 2 into f of x at I plus 4 minus f minus 5 by 2 into f of x at I. So into delta x cube equal to 0. So now in the question what format is it was given? It was given as, if we go and look, okay, d cube f by dx cube equal to minus 3 times of f of I plus 4 plus 14 times of f of I plus 3 minus 24 times of f of I plus 2 plus q into f of I plus 1 minus 5 into f of I, f at I, like f at I. So not f of, it is f at I. So it is divided by 2 into delta x cube. So here we are having some 2 as common. So now we will go and rearrange the equation in such fashion. So now we have f triple dash of x. So this equations we got. Now what we are doing, we are just taking the 2 common. So if we are taking 2 common, what will happen? It will become 18, it will become 24, it will become 14, and it will become minus 3 only, it will become minus 5 only. So it is 2 we have taken and we are just taking it to the other side, but doesn't matter. So we are asked to find the coefficient of f of I plus 1. So what is the coefficient of at f of I plus 1? It is 18. So 18 is the answer. So I hope it is clear now. So I hope it is clear. We will go through the question, problem once again, so that it will be like helpful for you. So what we are doing is that we are asked to find the value of a coefficient in the expansion of d cube f by dx cube. So we are asked to find. So for us to find that, we need to first know all the coefficients, then it will be easy for us. So we are just going through the step by step process. So I'll start from here this time. So this is the equation given, f triple dash of x minus, or else I'll rearrange it so it will be better for you. So this is the question, and what we are doing, we are just rearranging it in this particular format. So d cube f by dx cube equal to minus 3 at f of I plus 4 plus 14 at f of I plus 3 minus 24 at 24 into f of I plus 2 plus q into f of I plus 1 plus minus 5 into f of I divided by 2 times of delta x cube. So q is the unknown here. So we are just, what we are doing, we are just rewriting it as f triple dash of x, and this is on the other side, we are just taking it to this side, which side it doesn't matter, minus a naught into f of x at I plus 1, a1 into x at I plus 2, a2 into x at I plus 3, a3 into x at I plus 4, a4 into f of x at I divided by delta x cube. So we are rearranging in this format. For us now, we need to know f of x at I plus 1. So it is f of x plus f dash of x into delta x plus f double dash of x into delta x square by 2 factorial plus f triple dash of x into delta x cube by 3 factorial, and it goes on. We are taking till 4th term. Now we have x at I plus 2 as well. So what varies? It is I plus 1, here it is I plus 2. So here it is delta x, here it is 2 times of delta x. So delta x into, changes into 2 times of delta x. So f of x at I plus 2 equal to f of x plus f dash of x into 2 times of delta x plus f double dash of x into 2 times of delta x square by 2 factorial plus f triple dash of x into 2 times of delta x cube by 3 factorial, and so on. So we have terms expanded for x at I f of x at I plus 1, f of x at I plus 2, and also we have f of x at I plus 3 and f of x at I plus 4 as well. So what varies in other two equations is that here it is delta x, here it is 2 times of delta x. For x at I plus 3, we will have 3 times of delta x, and x at I plus 4, we have 4 times of delta x. So that is the variation. So I haven't included other two equations. So now we are substituting these things back in the equation. It becomes f triple dash of x into delta x cube. For ease, we are just taking delta x cube in the common and multiplying, plus this minus goes inside actually, minus a naught into f of x plus f dash of x into delta x plus f double dash of x into delta x square by 2 factorial plus f triple dash of x into delta x cube by 3 factorial plus f to the power of 4x into delta x to the power of 4 by 4 factorial. This is for a naught. Similarly, minus a1 into x at I plus 2 and minus a2 into f of x at I plus 3 and minus a3 into f of x at I plus 4, and last minus a4 into f of x at I. So we are just substituting the expansion in the original equation, and we are getting this. Now we are taking the factors common. So for f of x, we are taking the all the coefficients and rewriting the equations. We are just taking out the coefficient common factors and taking the coefficients. So separating the coefficients, we have f of x, these coefficients, f dash of x into delta x, we have these coefficients, and similarly for all we are rewriting the equations so that we are getting the this form. So now this is the left hand side. What is in the right hand side? Right hand side it is equal to 0. So we are just equating all the coefficients to 0. What happens is that we are having a0, a1, a2, a3, a4, and for 5 terms we have 5 equations and 5 unknowns we are getting. And when we solve these 5 equations simultaneously, we will get the values for these 5 variables, like these 5 coefficients. So from that we are getting the value of a0 as 9, a1 as minus 12, a2 as 7, a3 as minus 3 by 2, a4 as minus 5 by 2. So now we are substituting all the coefficient values back in the equation. So we are having f triple dash of x minus, it is common, so it is a0 into f of x at I plus 1 minus, this is plus a1, so here it is minus 12 into f of x at I plus 2 plus 7 into f of, that is a2 into f of x at I plus 3 plus a3 into f of x at I plus 4 plus a4 into f of x at I equal to divided by delta x cube equal to 0. So in the equation it is f triple dash of x equal to, so we are taking the terms back to the other side and we are taking the 2 in the denominator common. So this term becomes 18 and this term becomes 24, this term becomes 14, this term becomes 3 and this term becomes 5. Because 2 we are taking it as common in the denominator. So what is asked in the question? We are asked to find the coefficient of x, f of x at I plus 1. So the coefficient is 18. So it is f of x at I plus 1, the coefficient is q. Q is now we found out as 18. So 18 is the right answer, which is option D is the right answer. Now we are clear now. So now we will go to question 10. Okay. Convergence condition is about the equivalence between dash. Convergence condition is about the equivalence between dash. Option A, exact and the numerical solution of the partial differential equation. Option B, exact solution and the numerical solution of the discretized equation. Option C, exact partial differential equation and discretized equation. And option D, none of the above. So the question is about convergence condition. So in all the CFT problems, we want to attain the convergence, converged solutions we want to get. So what exactly is the converged solution or convergence? So answer is actually option A. It is the convergence condition is about the equivalence between the exact and the numerical solution of the PDE. So what happens is that we have PDEs, that is partial differential equations, from the continuity equations, momentum conservation equations, those equations, and we will be solving those equations to get the values of the velocity and whatever variables in those equations. Like in continuity momentum conservation equations, we have terms like rho v, v. So we are getting the values of those velocity fields or something. So it is about solving those equations and getting the values. So what do we think convergence is all about? It is the equivalence between the exact and the numerical solution of the PDE. Converged solution is that which it reaches the final condition. In that case, it is we get the exact solution, hoping to get closer to the exact solution. And there will be one solution to the partial differential equation, and from our numerical approach wherein we converted the PDEs into linear algebraic equations, and finally we are getting the solution for the linear algebraic equations through numerical methods. So the solution through the numerical method should be close enough with the exact solution to the original PDEs. So that is what convergence is all about. Convergence condition is about the equivalence between the exact and the numerical solution of the partial differential equation. So answer to this question is option A is the right answer. Option A, convergence condition is about the equivalence between the exact and the numerical solution of the partial differential equation. So as I mentioned, like we are using the numerical techniques to solve the linear algebraic equations which we obtain from the discretization of the system and the partial differential equations. So that numerical solution should be like giving the closer result to the exact solution. So it is all about the equivalence between the exact solution and the numerical solution of the PDEs, that is partial differential equations. So that is what we call it as convergence. Moving on to next question. Okay, convergence condition refers to the idea that as the discretization of the problem becomes finer, numerical solution should approach the exact solution of the original partial differential equation. That is what we see is that in finite difference or finite volume approach or finite element method also we use finer grids. So as the grid size becomes finer, we say that numerical solution should approach the exact solution. So that is numerical solution should approach the exact solution. That is the concept. Now we are going to next question. In question 12, it is about a grid independent solution is expected to agree with the analytical solution of the partial differential equation. Option A true, option B false. Okay, it is a true or false question. What is asked? A grid independent solution is expected to agree with the analytical solution of the partial differential equation. Answer is option B. False is answer. What is grid independent solution is that when you change grid size beyond a certain limit, right, the solution would not vary much. That is what we call as grid independent solution. That is, the solution is independent of grid size beyond that condition, beyond that limit or whatever. So that is what we call it as grid independent solution. That is, the solution is not varying much with respect to the grid size beyond that thing. So it is known as grid independent solution. So it is having no direct link with the analytical solution of the partial differential equation. So like not all grid independent solution is like, it is not expected. It is just a criteria to verify that your grid size or your mesh size is not influencing your solution. Till a particular mesh levels or grid levels, with coarser mesh or with finer mesh, your solution will be varying. But in the grid independent solution, that your solution is not dependent on the grid size. So that is what we say. So it has nothing to do with the analytical solution of the PDEs. So answer is false actually. Now we will go to question 13. In question 13, what is asked? Which of the following statements is true about Taylor series expansion of a function f of x at f of x about x naught? So which of the following statements is true about Taylor series expansion of function f of x about x naught? Options are, okay, first we'll read the statements. What is given is that first one, it is valid everywhere. It is valid everywhere. Second one, the first n plus 1 derivative of f of x need to be continuous in the interval. The first n plus 1 derivative need to be continuous in the interval. And third one, it is conditionally valid. Okay, so these are the three statements. So we need to identify which of the following statements is true. First one, what is given, it is valid everywhere. And what is asked, which of the following statements is true about Taylor series expansion of function f of x at about x naught. Taylor series expansion of f of x is not valid everywhere, rather it is valid in the close neighborhood of x only. So first statement is this statement is wrong. Second statement, the first n plus 1 derivative of f of x needs to be continuous in the interval. Again, this is true because it needs to be continuous. So that is the thing. So first n plus 1 derivatives of f of x need to be continuous in the interval. So second statement is true statement. First statement is false, second one is true, and third one, it is given it is conditionally valid. Again, that is also true. It is like valid with certain conditions only, right? It is not like valid at everywhere. So those things are not there. So it is conditionally valid. It is like conditions like it is valid in the neighborhood of x. Those things we use. So answer is it is conditionally valid. So third one is true. So first one is false, second one is true, third one is also true. We will now look at the options and identify which of them is correct based on this particular question. So option A, 1 only, option B, 2 only, option C, 2 and 3, option D, 3 only. Answer is option C, that is 2 and 3 is the right answer, because it is valid only in the neighborhood of some x and it is like a condition. So it is like a conditionally valid and it should be continuous in the interval. Like the first n plus 1 derivative need to be continuous in the interval. So Taylor series expansion is based on these conditions only. So option is option C, which mentions that second and third statements are right. So the right answer is option C is the right answer. Option C. Now we'll go to question 14. In question 14, which of the following statements is false about non-uniform grids on a structured grid? So non-uniform grid on a structured grid, we saw the one example in figure 4 itself, wherein the spacing was not uniform but the grid was a structured grid. So now the question is about which of the following statements is false. It is about identifying the false statements. So now first statement is that they are rarely used. They are rarely used. Second one, it is not possible to derive. It is not possible to derive finite difference approximation of accuracy higher than second order accuracy. So what is asked? They are rarely used. It is not possible to derive finite difference approximation of accuracy higher than second order accuracy. And we'll see third. Okay. two statements are only given, and we are asked to find which of the statement is false actually. First one, it is they are we'll see the options first. Option A, 1 only. Option B, it is 2 only. Option C, both 1 and 2. Option D, neither 1 nor 2. So the question is about which of the following statements is false. Read the question carefully. It is about asking which of the following statements is false. So first statement, if we look at, it is mentioning they are rarely used. That is, non-uniform grids in a structured grids is being rarely used. So that statement is a false statement. Like, it is not rarely used, rather it is used whenever required, based on the geometry, based on the conditions. So it is used whenever required. So that statement is a false statement. And in the second one, it is mentioning that it is not possible to derive finite difference approximations of accuracy higher than second order accuracy. Again, this is false. This statement is false statement. Again, this statement is false because it is false that it is stating that it is not possible to derive finite difference approximation of accuracy higher than second order accuracy. This is false because, like, third order, like, order, whichever order is higher order can also be derived, and it is possible. So it is a false statement. So the question is about identifying the false statements. So both the statements are false statements. So answer is option C is the right answer, because both the statements are false statements. Both 1 and 2 is the right answer. Which of the following statements is false? So read the question carefully. It is asking us to identify which of the following statements are false about using non-uniform grids in a structured grids. And the first statement given is that they are rarely used. That is a wrong statement because it is used whenever required. And second statement, again, it is stating that it is impossible to derive higher order approximations for higher order accuracies. Again, it is false. So both the statements are false. So option C is the right answer. Answer is option C. That is, both 1 and 2 are false statements. Now we will go on to question 15. Okay. Question 15 states that the truncation error in a finite difference expansion is this one. That is, truncation error in a finite difference approximation is minus of dou square u by dou x square into delta x by 2 minus dou cube by dou x cube into delta x cube by 6. So what is the order of accuracy of the finite difference equation? So truncation error in a finite difference approximation is given by this: minus dou square u by dou x square into delta x by 2 minus dou cube u by dou x cube into delta x cube by 6. So what is the order of accuracy of the finite difference equation? So the power, like, the this one is the determining the order of accuracy, and the power raised to that is 1. That is, delta x is 1 over there. So answer is actually 1. We'll see the answer actually. Option A 1, option B 2, option C minus 2, option D minus 1. So actually the definition of order of accuracy is that order of accuracy of a finite difference approximation It refers to the power of the step size, that is power of delta x, or if this is minimum whatever it is there, that power is the order of accuracy. If here delta x square is there, it is second order accuracy. So it is the power of this delta x, or like if it is delta x square minimum power, like here delta x is there, delta x cube is there, but it is a minimum power, so delta x is the gives rise to the order of accuracy. So it is 1 here, like, or truncation error. From the truncation error we can say that delta x cube is there, but the minimum power of the delta x, or the step size whatever, so that gives the order of accuracy. So it is option A, that is 1 is the right answer. Sorry, option A, 1 is the right answer. Now we will go to question 16. In question 16, we are given 4 figures A, B, C and D. Which of these diagrams represent the central difference approximation of dou u by dou x? So we have 4 figures actually, and we need to identify central difference approximation of dou represented by dash. So central difference approximation involves I minus 1 and I plus 1 the term. So if we look at figure 1, here I minus 1 is there, but I plus 1 is not included. And similarly in figure B, it is I plus 1 is not included, and C, it is I minus 1 is not included, whereas D, it is included. So answer to this question is option D is the right answer. Now we'll go to question 17. In question 17, what is asked is that we are given one figure, and in figure what is given that u1 is 0 meter per second, and at point 2 we have u2 which is 5 meter per second, and the distance between 2 points is 0.5 centimeter, half a centimeter distance between 2 points, and the velocity difference is u1 is 0 meter per second and u2 is 5 meter per second. Find dou u by dou r at point 1 using forward difference method. So we need to find dou u by dou r at point 1 using the forward difference approach. So options are option A 1000, option B 100, option C 500, option D 5000. So dou u by dou r using forward difference approach, how can we get? It will be like u at if we go with u at r plus delta r minus u at r divided by delta r, right? So u at r plus delta r minus u at r divided by delta r. So delta r here is 0.5 centimeter. R plus delta u at r plus delta r is 5, and u at r is 0. So 5 minus 0 divided by 0.5. So 5 and 0 are in meter per second and 0.5 is in centimeter. So it is 5 divided by 0.5 into 10 power minus 2, and it will be like 1000. So answer is option A. Option A is the right answer. Find dou u by dou r at point 1 using forward difference method. So answer is option A, because dou u by dou r, it is, we can calculate it as forward difference approach. We use it as okay, u at r plus delta r minus u at r divided by delta r. So now it is clear, more clear. Find dou u by dou r at point 1 using forward difference method. So answer is option A. How? Dou u by dou r equal to u at r plus delta r minus u at r divided by delta r. So equal to u at r plus delta r is 5 minus u at r is 0 divided by 0.5. Delta r distance is 0.5. So 0.5 centimeter. So it is 0.5 into 10 power minus 2. So we are getting 5 cancel and 10 power minus 3 will be there at the denominator, and when it goes up we get value as 1000. So answer is option A. Now we will go to question 28. Sorry, question 18, not 28. Question 18. In question 18 what we have got is that Lack's theorem states that dash. Option A. Convergence is assured for well-posed linear initial value problems. Option B. Stability is assured for well-posed linear initial value problems. Option C. Consistency and stability are sufficient for convergence for a well-posed linear initial value problems. Option D. None of the above. So the question is about what Lack's theorem is all about. So here Lack's theorem states the convergence condition. Convergence condition. So how it is stating is that first one, it is actually convergence is assured for well-posed linear initial value problem. It is false, and stability is assured for well-posed linear initial value problems. That is also false. Third statement is the right statement actually. Consistency and stability criteria are sufficient for convergence for a well-posed linear initial value problems. So when consistency and stability conditions are satisfied, convergence will be satisfied. So that is what is meant over here. Lack's theorem states that consistency and stability are sufficient for convergence for a well-posed linear initial value problem. So option C is the right answer. Answer is option C. So what Lack's theorem states is that Lack's theorem or Lack's equivalence theorem says that a finite difference approximation for a properly posed partial differential equation satisfying consistency and stability possess necessary and sufficient condition for convergence. So for a finite difference approximation for a partial differential equation, properly posed partial differential equation, when it satisfies consistency and stability, these two are necessary and sufficient condition for convergence. So what is consistency over here? So the truncation error approaches 0 when time step size and mesh size goes to 0. So when we are defining the time step and mesh size, right? If it goes very small, truncation error also goes very small. So the truncation error term, it is like we are neglecting certain terms, right? Delta x to the power of delta x to the power of 3 or delta x to the power of 4. Depending on the order of accuracy, we will be neglecting those terms. So if delta x in that condition is very, very small, like 10 power minus 3, 10 power minus 2, something like that. If it goes to the power of 3 or if it goes to the power of 4 again, that error term becomes 0. You can imagine, right? 10 power minus 2 to the power of 2, like it becomes 10 power minus 4. So it is a small value. So the truncation error, it is going on decreasing with decrease in the time step size or mesh size, depending on the derivative term. Whatever it is reducing, uh, time step or a mesh size delta x or delta t. When it reduces, the truncation error terms also reduces and it approaches zero, like very fine mesh, it approaches zero also. So consistency condition is satisfied. Now comes the stability. What is meant by stability? It means that the error goes on reducing for every time step to time step. Like for the calculation is proceeding. So when the calculation is proceeding from one time step to another time step, the error should go on decreasing. Error should not keep on increasing. If that is the case, it leads to unstable solutions and it's not a proper thing. So these two conditions are keeping a check on something, that error is reducing and also some criteria is being maintained. So we say that convergence will be assured for in such cases. Convergence is assured when we are using when we are already satisfying consistency and stability. If we are satisfying consistency and stability, these two possess necessary and sufficient condition for convergence. This is what is stated in the Lax theorem. So if we go back, Lax theorem states that consistency and stability are sufficient for convergence for a well-posed linear initial value problems. So option C is the right answer. So now we are going to question 19. So in question 19, what is being asked is that for the expansion given by for the expansion given by equation A to be convergent, which of the following condition needs to be satisfied? For the expansion given by equation A to be convergent, which of the following needs to be satisfied? So first one is that we'll see the equation A first. So equation A is nothing but f of x at f at x plus delta x equal to f at x plus a into df by dx plus b into d square f by dx square plus c into d cube f by dx cube plus d into d power 4 f by dx power 4 plus e into d power 5 f plus dx power 5. So this is the equation A, and for the expansion given by equation A to be convergent, which of the following condition needs to be maintained, needs to be satisfied? So we will see that option 1, small delta x, option 2, f to be continuous, and option 3, f to be differentiable. So as we all know, for Taylor series expansion, the delta x should be small and f to be a continuous, and also it should be differentiable. So all three needs to be satisfied for A to be convergent. We'll see the options first. Options are option A, 1 is sufficient, option B, 2 is sufficient, option C, 3 alone is sufficient, option D, all 3 are necessary. So as I mentioned, right, this is given by Taylor series expansion. So for the Taylor series expansion to be convergent, we need all three conditions. Like it should be small, the delta x should be small. So and f should be continuous and f should be differentiable. So for example, why I'll tell you this, we have some function we have some function like this. Okay, if we are sorry okay, now we have some function like this. If we are having smaller delta x, we will go from here to here, 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 and here to here, and we'll get a proper convergent solution. Rather, for the same function, if we jump from here to here, imagine our solution will be something like this. It won't be like this. Here we are just going from here to here, here to here, we are getting the exact thing. But if delta x is small, we cannot get the solution. And again, it should be continuous function and it should be a differentiable function. Only then we can use this. So all three are necessary is the right answer. So 19 question option D is the right answer. Now we'll go to question 20. Question 20, it is about consider the equation dou u by dou y equal to u at I comma j minus u at I comma j minus 1 divided by delta y. So consider the equation dou u by dou y at I comma j equal to u at I comma j minus u at I comma j minus 1 divided by delta y, formulated using Taylor series expansion. Find the type of equation. So this is actually first order backward difference equation. So if we remember, we can say that it is like using I comma j and I comma j minus 1. So since it is varying derivative with respect to y, j factor is varying. So j and j minus 1. So it is a backward difference formula and it is a first order thing we know. If it is j plus 1 and j, that is a forward difference approach. But right now it is a backward difference approach. So we'll see that it is a first order forward difference. Option B, first order rearward difference. Option C, second order forward difference. So option D, second order rearward difference. So here rearward is like backward only. So by considering the equation, we are just stating that it is like using j point and j minus 1th point. So it is a backward difference. And if we write Taylor series expansion for f of x minus delta x or f of y minus delta y, what will we get? F of y minus delta y equal to f of y minus dou f by dou y into delta y, or else I'll go there, plus dou square f by dou y square into delta y square by 2 factorial, right? In the first few slides we have seen, right? It is like f of y minus, okay, let it be x, we'll just see x minus delta x equal to f of x at x minus dou f by dou x at x into delta x plus dou square f by dou x square into delta x square by 2 factorial. So now what we are doing is that we are taking this term to the other, okay, not this term, we are taking this term to the other side and this term to this side, f of x minus f of x minus delta x, and we are dividing it by delta x, right? We are dividing it by delta x. So what is remaining? It is like we are dividing it by delta x square by delta x. So dou f by dou x equal to f of x minus delta x divided by delta x. So we are dividing the whole equation by delta x. So what these terms come as the truncation error. So what is the power of the step size here? Because we are dividing it by delta x, it becomes delta x square by delta x, it becomes delta x. So what is the power? It is 1. So it is a first order. So it is a first order backward difference approach. So that is the thing. So consider the type of equation dou u by dou y at I comma j equal to I comma u at I comma j minus u at I comma j minus 1 divided by delta y. Find the type of equation. So if we solve equation, and we will know that it is a first order and it is a backward difference approach. So first order backward difference. So option B is the right answer. Answer is option B. Now we are looking at the last question for today's session. So question 21, what it is stating that Consider the following expansion of f about point I. Okay. Okay, f of x plus delta x equal to f of x plus a into df by dx plus b into d square f by dx square plus c into d cube f by dx cube plus d into d power 4 f by dx power 4 plus e into d power 5 f by dx power 5. So this is equation A. So we are considering the expansion of function f about point I, and value of b in equation A is dash. So what is the value of b in equation A? So what is Taylor series expansion stating? F of x plus delta x equal to f of x plus dou f by dou x plus dou f by dou x into delta x plus dou square f by dou x square into delta x square by 2 factorial plus dou cube f by dou x cube equal into delta x cube by 3 factorial and so on. So this is a Taylor series expansion. So consider the following expansion of function f about point I. So what is the value of b in equation A? So it would be about delta x square by 2 factorial should come. So option A it is 2 factorial, option B it is 1 by 2 factorial, option C it is 1 by 4, option D it is none of the above. So it is about none of the above is the right answer, because we are not specified of the value of delta x, we cannot directly take it as 1. So it is given that x is point I, but we have no information about delta x. If delta x is given as 1, it would be 1 by 2 factorial. But since it is not mentioned anywhere that information, we cannot directly assume it. So answer is none of the above. So option D, none of the above is the right answer, because f of x plus delta x is equal to f of x plus df by dx into delta x plus d square f by dx square into delta x square by 2 factorial. So delta x square is missing. So it is wrong. It is not present anywhere. So answer is none of the above. So option D is the right answer. So yeah, thank you. That's all for today's session. If there are any doubts, you can ask now. We will see. Again, we will meet next week at the same time, 3 p.m. to 5 p.m. and discuss problems associated with week 6. So that's it for today's sessions. If you have any doubt, you can ask. In today's class, we have seen about the finite difference approach and mostly Taylor series. Those things we have seen. If you have any doubts, you can ask now. Thank you. Okay, thank you then. I am closing the session. If there is no doubts, I will close the session. Thank you.